During the construction of the world's tallest cable-stayed bridge, engineers faced a major challenge of connecting the road sections suspended between two towering pillars. Each road section weighed as much as 25 locomotives, and there were a total of 8 sections to be placed between the pillars. There was no crane in the world capable of reaching a weight of 5,000 tons to a height of 800 feet between these two pillars. If a crane were placed atop the pillars to pull the road sections, the structural integrity of the pillars, given their height, could easily be compromised. The taller the pillar, the weaker its top would be. This issue was nothing short of a nightmare for the construction team. The construction of the Millau Viaduct, the world's highest cable-stayed bridge, was a marvel of engineering, standing at a height of 1,125 feet above ground level. It surpassed even the Eiffel Tower by 45 feet. The bridge was so high that it often appeared to float above the clouds. The construction company undertaking this project faced relentless challenges, with fines amounting to $30,000 being imposed daily. Landslides and stormy winds at speeds of 130 km per hour were making the work nearly impossible. Never before had a 4-lane highway been built at such a height, and no one had dared to attempt it because everyone knew that pushing engineering limits was not just crossing boundaries but defying them. On the other hand, the construction of this bridge became imperative for the French government in the 1980s. The traffic from northern France to Spain had to descend through winding roads and then ascend again, causing traffic jams for at least 6 hours in Millau City. To facilitate tourists, the French government had no option but to construct a direct motorway from Paris to Spain, bypassing the complicated terrain of mountains and the Tarn River. However, this was easier said than done. The bridge had to be almost as tall as the mountains, and this was a feat considered nearly impossible. At that time, the world's tallest bridge was the Golden Gate Bridge in California, a suspension bridge where the road was only 250 feet above water surface, nothing compared to the 6 times the height of Milau's mountains. Many experts believed that a bridge over Millau was inconceivable, and even if such a bridge were built, it would inevitably invite a major disaster. Despite these doubts, when traffic jams reached critical levels, the French government had no option but to face this bitter pill. From design to construction, the engineering team had to overcome 3 formidable challenges: erecting the tallest bridge pillars in the world on sloping terrain, placing a 36,000-ton 4-lane highway on top, and erecting steel pylons on the bridge, each heavier than an Airbus A380. All these tasks had to be performed hundreds of feet above ground. For this monumental task, the world's best architect, Lord Norman Foster, was hired. He had already made a name for himself with his designs worldwide. The task was to design a bridge as delicate as a butterfly but strong enough to withstand thousands of tons in swift winds. A single mistake in this design could spell disaster. After years of hard work, Lord Foster presented a magnificent design. 7 bridge pillars were designed, with the road curving over them. However, the main challenge was that pillar number 2 had to be the tallest, while the remaining 6 pillars would be on a slope. Transforming this unique design from paper to reality was no easy feat for the construction team who dared to undertake this bridge. The construction of the Millau Viaduct faced numerous challenges. Just as they were starting, geologists discovered fractured limestone under the area, creating cavities that had to be addressed. One significant issue was the risk of landslides during drilling and excavation. Despite these warnings, construction began, but a dramatic event unfolded. A dangerous landslide covered the foundation pillars with rocks. Fortunately, there was no major damage. The construction team stabilized the slope with cement and continued the project. Building the viaduct's 7 massive pillars required nearly 200,000 tons of concrete, so a factory was established on site to produce reinforced concrete. This material, which included 16,000 tons of steel bars, was essential for the project. Interestingly, The same steel used for the Millau Viaduct could cover a distance of 4,000 kilometers, from Dubai to China. The engineers faced challenges with the shape of the pillars. Each one had a non-uniform shape, with a base wider than the top. They used a technique where a heavy steel frame was formed and then filled with concrete. Casting each pillar took longer than anticipated, more than 6 months per pillar. But the engineering challenges didn't end there. The location accuracy of each pillar was critical. Even a slight deviation could affect the alignment of the road section placed above. To ensure precision, GPS technology was used extensively. Multiple satellites helped pinpoint the exact location for laying the foundations, casting the pillars, and placing the road sections. Despite these efforts, the team faced challenges during the construction phase, requiring innovative solutions to ensure safety and accuracy. The most critical phase was constructing the road sections between the pillars at a height of over 250 meters. Any error during the sliding process could result in catastrophic failure. To address this, a hydraulic ramp system was employed, synchronizing the movement of each road section to push them forward gradually. The success of this innovative approach minimized risks and allowed the construction team to complete the daunting task of building the world's tallest bridge. The Millau Viaduct stands as a testament to engineering prowess and ingenuity, overcoming significant challenges to create an iconic structure. The reason behind this was simple: strong winds could easily bring down the bridge, especially when a road section hangs in the air without support. In 1940, in Washington state, the pillars of the Tacoma Narrow Suspension Bridge were holding back the air, and as a result, the entire bridge started swinging badly. Just a few days after its launch, the entire bridge collapsed into the water. Days passed, and the work of placing the road section on the pillars was proceeding loudly. By 2004, road sections had been laid on both sides. Now only the upper part over the river was left. If this final section didn't sit properly, all the hard work would be multiplied like zero. The road is also curving in this section, so it's very important for its pinpoint to sit in place. At this moment, the whole of France was watching the live broadcast while the French Prime Minister himself was present at the scene. The hydraulic ramp button was pressed for the last time. In 4 years, the roads of the north and south sections had been connected accurately. A 90-meter high steel pylon was also placed for extra support after the roads were connected. One pylon weighed 700 tons, and there were 7 such pylons. It was the first time in the world that such heavy pylons were placed at such a height. The total weight of just the road section with the wire duct is 40,000 tons. After that, a concrete road was laid on top of it, adding 10,000 tons and making the total weight of the road 50,000 tons. To give you an idea, this weight is equivalent to 1,200 battle tanks or a large cruise ship. To check its strength, 28 trucks have passed over it at once. It's surprising that the road section, designed to swing up to 50 centimeters, was only 25 centimeters off due to the weight of all these trucks. The Millau Viaduct was open to the public for the first time on December 16, 2004. This was the result of the engineering team's hard work day and night, not only successfully constructing the world's tallest bridge but also finishing the work before time and setting a new record. I hope you'll also like and share this video from Jam TV. Thank you very much for your love-filled comments.